So welcome back to part 4 of solving linear simultaneous equations, and this section or part is called solving AX equals B with weights and constraints. So let's go straight in with an example to try and see what we're talking about. I think in the very first part we looked at fitting a straight line to a set of points, and we tried to minimize the sum of the error terms squared. So what happens if we get a point n plus 1, which is a bit of an outlier? So it could be something wrong with our equipment, or it's just a particular measurement which doesn't represent the trend at all. If we incorporate that into our least squares solution, then we could get a line like this, the green line. So to accommodate that outlier, the green line is moved like this, and it doesn't represent all of the other points. So one way around that is to actually form a new objective function and give a very small weight to that point. So in terms, a small weight to that error term. So in terms of trying to minimize j, what will happen there is that will have very, very little effect on the overall j, and so this green line will then move up to this position. So if you know which points are going to be outliers or slightly in error, either due to calibration or measurement or whatever else, then you can weight those individual points, as I've just shown you. Okay, so let's take a simple example here. Go back to these familiar equations. So what we do if we want to weight the error terms, we can simply take the E transpose times E, which would give us the sum of all the errors, and multiply it, or put in the middle a weighting matrix, which is a diagonal matrix, so all the other elements are 0. And we'll write it like this. So it's the norm, the 2 norm, but we put a W at the bottom. 2 norm squared, we put a W at the bottom to tell us that it's got this weighting matrix in the middle. If W is equal to I, we just get the normal norm squared. So we try to minimize that, and again, if you minimize that by the way we've looked at many times, expand it and then differentiate with respect to x, you end up getting this expression. And if you put W equal to I, so there's no weighting whatsoever, you get the familiar least squares expression that we're all familiar with. Okay, so that's weighted least squares. Now let's have a look at weighted least squares, or in fact just least squares with regularization, or what's called shrinkage. So we have problems with the above solution, weighted and non-weighted. And this occurs in particular in machine learning, and it includes non-uniqueness, overfitting, and ill-conditioning of A. So let's have a look at what we mean by that. Non-uniqueness is that when we get an infinity of solutions either to the least squares problem or to the AX equals B problem. Another case is overfitting. You remember that, where we actually start trying to model the noise more than the actual trend itself. And finally, we've got something called ill-conditioning of A. So if you take the matrix A and you look at the spread of its singular values, if that's very large, then what that can mean is that, and we're going to look at this later on, if you have a small error in, say, the observation B, that can give you a very, very large error in X. So you get this huge error amplification. So that's ill-conditioning of A. And without going into it in any more depth, because there are lots of papers written about this and YouTube videos, one way around that is to do what's called regularisation. So we're going to look at L2. So L2 refers to the L2 norm, regularisation first of all. And what we do is we take this argument here that we're trying to minimize, and we add this extra term. Rho is some constant, and we multiply it by the norm squared of x. So what we're doing here is, if rho is 0, there would be no regularization. If rho is very, very large, then what it's telling the algorithm is it's saying, you know something, you get a lot more bang for your bucks if you manage to reduce the norm squared. And so it will constrain this norm squared to be quite small. And you have to choose the value of rho from the particular application that you're dealing with. And if you differentiate that again, you end up getting this expression. So it can be shown that regularization can deal with these issues above. Certainly it can deal with this issue because there's no question of this not being invertible. This will always be invertible now because of this structure, this form. So let's have a look at the different types of regularization and the norms that they actually use. So here's a situation where we're going to use the L2 regularization. This is L1. This is called elastic net regularization. This is L0 regularization. The L1 is also known as lasso. That's quite famous and quite well known. Let's quickly review these norms. So LP norm is defined as this. You take a vector x and put a p down at the bottom here. That means it's the p norm. That's why I've changed this to putting a 2 at the bottom to remind you that this is a 2 norm. So I've just slightly changed the nomenclature here. So the L1 norm is putting that to 1. It's quite clearly the sum of the absolute values. The L2 norm is the sum of the absolute values squared. The L0 norm, which is not really a true norm, but if you accept this definition, then you end up getting the sum of the number of non-zero terms. So it's the number of non-zero terms in the vector x. And the L infinity norm, which isn't used here, is the maximum of all the elements, the modulus of all the elements. So that's the max. So let's look at the different types of norms that are used in the regularization. And if we plot the L2 norm, say plot it equal to 1, we get a circle in the x1, x2 plane. If we plot the L infinity norm, and don't forget what the L infinity norm was, it was the maximum of the modulus of x1, modulus of x2. So if we go around that contour, we find that the L infinity norm is always equal to 1. It's clear to see that. And if we do the L1 norm is the sum of modulus of x1 plus modulus of x2. All along that contour, if we set that equal to 1, we get 1. So let's look at the problem that we're dealing with. We're trying to optimize or minimize that particular objective function. Here are the contours of that two-dimensional quadratic. And here is the regularized least squares when we're using the lasso regularization or lasso regression. So if we make alpha very large, then this term becomes more significant in terms of trying to minimize that rather than this. Now, the important thing to notice, and I'm not going to go into this in much detail because there's a lot of stuff written about lasso and it's way above the tutorial level of this particular video. But because this contour allows you to have x1 equals 0 or x2 equals 0, it is possible in this case that you get XRLS, this particular solution vector, which will be sparse, i.e. it will have zeros in it, many more zeros than if alpha was equal to 0. And that sparsity has many implications, which you can all go online and read about if you're interested. Okay, so now let's go and have a look at how we might use weighted least squares in something like digital filter design. And I've taken this because it's a simple example. It's not the way that you would really design a digital filter now, but it's pretty instructive about how you use weighted least squares. So you don't need to know much about digital signal processing. All you need to know is that the frequency response of the filter is given by the impulse response of the filter. And the impulse response is convolved with the discrete time input to give you the output y of n. The transfer function or frequency response is given in this particular case for an even symmetric impulse response is given by this. Normally this is complex, but in this particular case when it's even symmetric, we're going to have just a real transfer function. And what we'd like to do is we'd like to specify that transfer function, say yes, we want it to be low pass, high pass, band stop. And so what we do is we say let's sample the actual frequency response and put it equal to desired values. So what we end up having is p desired values. So we put that equal to p desired values. And what we say, what are the H values? What are the impulse response coefficients in order to realize that desired frequency response? And that turns out just to be a least squares problem. So here we have the response, and here we have the desired response. So this is the desired response, these black dots, okay? And we go from 0 up to 0.5. Again, if you don't know much about DSP, this is really like the normalized frequency response. 1 is the sampling frequency and 0.5 hertz is the half the sampling frequency. Okay, this is the pass band. This is the stop band, so this will be the transition band. The stop band is from, this is the beginning of the stop band, which goes from there up to 0.5. So what you can do is you can write the requirement that at these desired points you get the actual response that you want from the filter itself. And you can simply write it like this. There's n plus 1 coefficients in the filter that you're trying to design, and these are the desired frequency responses. So it becomes AX equals B. And the weighted least squares solution, that is, if you weight each one of the error terms, as we discussed before, you have this W matrix, which is the diagonal matrix, which gives the importance for each desired frequency bin design error. Okay, so let's take an example here and let's see what we've got. Here's the parameters that we're using. We're taking 200 points up from 0 up to 0.5 hertz. We've got n equals 10, so that means we've got 11 coefficients that we can play around with. The end of the pass band is 0.2, the beginning of the stop band is 0.25, and we've put equal weighting for all of the 3 bands. So if we go and solve that and see what we get, so there's no weighting at all basically, we end up getting this result. And this is not really very good because you can see the amount of attenuation that you're getting in the stop band is below minus 30 dBs. So that's pretty bad. So let's see if we can improve it by changing the weightings. So what we've done now, I'll put in red wherever I've made a change. We've reduced the pass band weighting to 0.1 and we've increased the stop band weighting to 1000. So we're saying any errors in the stop band are much more important than errors in the pass band. So look what happens. So when we do that, this is what we get with no weighting. When we introduce that weighting, we improve the stop band attenuation because the desired attenuation is 0. So it's saying it's much more important because of this weighting to reduce the stop band. And we're going to have a little bit of ripple in the pass band because we've reduced the weighting for the pass band. Now what I've done there is I've kept the pass band weighting the same, but I've increased the stop band weighting to 100,000. So we're saying it really is important to sort out that stop band. And we're not that concerned with the pass band. So what happens now when we get a lot more ripple in the pass band, but we get a lot more attenuation in the stop band. So what if I wanted to get a realistic response that would actually be of some use? So what I've done here now is I've said, okay, well, another thing that you need to change as well is you need to change the order of the filter. That is, more coefficients gives you more degrees of freedom. And we have, in this case, we'll have more points, 400 points, so we can get better granularity. We're going to have a stop band, which is 0.201. So it's very close to the end of the pass band. And we're going to keep the weightings the same here. 100,000 in the stop band and the transition and pass band are both 1. So if you look at what happens now, this is the case with no weighting and this is the case with weighting. And the ripple in the pass band is very little. And the reason for that is because you've got so many coefficients that even though you've increased the stop band weighting, you still don't get a lot of ripple because it can almost attain what you set out to attain in terms of meeting the requirements in the pass band. I should just say that this is not the way you would design a filter in DSP. There are many more sophisticated ways of doing it, but this is a good example just to show you how weighted least squares works in practice. Okay, another issue is solving AX equals B with constraints. So let's take an example of what's called antenna array beamforming. So what happens in antenna array beamforming? You have a set of antennas and they are picking up electromagnetic or RF signals, and they weight the signals coming in on each antenna with these weights. These weights in general would be complex, and then you get the output here. And the gain of this array in terms of theta is the direction in which you look. So 0 degrees is looking straight on down what's called the bore side. So in this case we've chosen W0, W1 and WL, L plus 1 coefficients, and we chose them in such a way that we're looking in a very, very narrow band at 20 degrees. So anything that's coming in from 60 degrees is going to get really attenuated, from 40 really attenuated. We've kept this main lobe very, very narrow, so we want to point in just one direction. And if we want to change the angle in which we look, we simply change these coefficients. In the old days, the way you do it is you'd have to move the antenna array around, physically move it around. But with signal processing, you can do this by just simply changing the weights. Now, what happens if we have a source coming in and we have interferers? So we have enemy interferers trying to block our reception, and we have a source where we know what theta 0 is. So we know what that is, but we don't know the direction of the interferers. So we want to set the weights so at the source direction no one passes undistorted. It's simple to do that, to point in the theta 0 direction. But we want to do something else. We want to null out the interferers, even though the number and direction is an unknown. So we set ourselves a criterion. We say, look in this direction, but minimize the power coming out, subject to looking in this direction. So the only way you can minimize the power coming out is to try to null out these interferers, and that will happen automatically because this system is data adaptive. So here's an example. This is the gain at angle theta. So we know the wanted signal is coming from there, and we've got two interferers. We don't know where the interferers are coming from. And so what will happen, one example might be, you might get this sort of response where you'll get a gain of 1 for the wanted signal, and for these interfering signals you'll get nulls. If the interfering signals are sort of small, it may not go to 0. It may think it's not worth its while going to 0, but if they're quite large, it will definitely null them out, because it's, as I say, it's minimum variance. You're trying to reduce the power of the output. So that's an example of using antenna array beamforming. So let's have a look now at the mathematics of solving AX equals B with constraints. We're not specifically referring to the previous example. I'm just giving you a general overview. So we're trying to minimize that objective function. That's well known, but we're doing it subject to this constraint. That is, we want the value of x to lie on this plane. So that's the equation of a plane. If I put C3, C4, Cn equal to 0, then this would just be a straight line. So here's an example of where it is exactly a straight line. So what we do is, you can imagine taking that straight line and then sort of moving upwards from that straight line in a plane, and it's going to slice through the two-dimensional quadratic, and you'll get this sort of slice, as it were, going through here. And what you're looking for is the minimum on that red line. So that gives you the constrained solution, and that's the true least squares solution. So that gives you a visualization of what's actually happening. And the way you do that is you rewrite J in this form. So I'm not going to prove this for you, but this is the way you can do it. And this again is the PA is the projection matrix, and this is the projection onto a space orthogonal to the column vectors of A. It's defined down here. So all you do is you add the constraint and you differentiate. So if we go through that, you add the constraint and differentiate. Here's the constraint added, so you're just forming the Lagrangian. And lambda in this case is a scalar. And if you go through and differentiate, you get the constrained solution is equal to the least squares solution minus this term here. So that's the solution to a linear constraint to minimize that objective function. And there's a summary of it. So let's do an example. Let's take A and B and C and Q like that, okay? And if I want to visualize what's happening, there's my constraint. and what I end up finding is that the point that solves this, so what you're doing is you're moving along this line and you're saying what point along this line minimizes the objective function. Okay, so you're going to get a worse minimum than if you were doing it with no constraint. And there's the least squares solution, and there's the constrained solution. Okay, here's a variation on what we just looked at. What if instead of saying that we're constraining the solution to lie on this line, we say we're not constraining it to lie on the line, but we're constraining it to lie around the line, and we can choose how close to the line we want to constrain. Now, that mathematically would be quite difficult, but we can do it in a sort of fudge the solution away. What we can do is have a fuzzy constraint. And we can do that, as we're going to see, by incorporating the red constraint line as an extra equation into ax equals b, and then actually weight that particular equation to say how important it is that it lies on that line. Now that's slightly different than constraining it to lie on the line. We're saying, well, we'd like you to lie on the line, and would you please lie somewhere near the line? And how much we want you to lie near the line depends on how much we weight that equation. Let's have a look and see what that means. So there's the A and B, and there's the linear constraint. So what we do now is we add that linear constraint into the A matrix. We add it as an extra equation. So there's x1 plus x2 equals minus 2. That's the constraint. And then what we do with that constraint is we put in our weighting matrix where we weight the constraint with a coefficient w. So if w is equal to 0, there's no constraint whatsoever, and we get the normal least squares. The larger we make w, the more important we say it is to be close to that constraint, so moving into that fuzzy red area. So let's have a look at that. So what we've done here is there's the w matrix, and what we do is we're going to change this value w. So when w is equal to 0, the solution that we get for the weighted least squares, when w is equal to 0, we're ignoring the constraint completely, and so we get the least squares solution, which is up here. Now, if we make w equal to 1,000, what we're saying is, wow, it's really important that you incorporate that constraint in. And so in that particular case, it's going to lie almost down here on that line, almost on that line. And as you change the value of w, as you start to reduce w, you say the constraint is less and less important. So as w goes to 100, 10, 5, 3, 2, 1, 0, that's what happens. You move away. So that's a sort of fuzzy constraint where you say how important it is that you are close to that line. And there are other applications for this particular method. Okay, so again, that blue line is the solution parameterized by w along a straight line. So let's look now at the other type of constraint we could have, which is quadratic constraints. So here we have a general quadratic constraint where C is a matrix and Q is a scalar. And again, to visualize, imagine we had a quadratic constraint which was a sort of circle, then moving it up like a cylinder, see how it cuts this objective function surface, and you might get something like that. So there's the solution for the constrained optimization, and there's the least squares solution. So take the case of b equals 0, because that makes it simple to get a solution to. In that particular case, again, we just add the constraint in here with the Lagrangian parameter and differentiate, set equal to 0, and we get this. So you might recognize this. If there was no C there, this would just be a eigenvalue problem. But because there's a C, it becomes what's called a generalized eigenvalue problem. These become generalized eigenvectors and generalized eigenvalues. And it's not difficult to show with the constrained optimization. the value for the constrained optimization x is equal to x min, where x min corresponds to the lambda, which is the minimum of all the eigenvalues. So basically you look for the minimum eigenvalue, look for whatever that x is, and that gives you the constrained solution up here. Okay, that's the end of section 4, and we're coming to the final section where we're going to look at just 2 last examples where we can use everything that we've learnt. So I'll see you in part 5.